Hey, this video is to finish up talking about the concept of a limit from an informal point of view and to get you where you can start doing some algebraic problems. So there's some homework questions that you should be able to do after you're done watching this video. And also we'll quickly go over why this sort of informal guessing method of looking at limits is not really sufficient and why we need something more. Okay, let's start. All right, let's look at the function f of x equals x squared, and let's consider the limit as x approaches 5 from the left of this function. And to consider that limit numerically, we'd be considering numbers like 4.9 and 4.99 for x. And what if x was 4.9999999? Then what is f of x? Well, it's 4.99999 squared. And I don't really want you to take 4.99999 and multiply it by itself. That's a ridiculous lot of work. But just thinking about it intuitively, 4.99999, just a tiny, tiny bit less than 5. And so you'd imagine that when you square it, you get some number just a tiny, tiny bit less than 5 squared, which is 25. And the closer that we get to 5 from the left, in other words, the more 9s we add, 4.9999999, etc., the closer we should get to 5 squared, or 25, and that's the concept that the limit as x approaches 5 from the left of this function is actually 25. And similarly, we can consider the limit as x approaches 5 from the right of this function and do the same thing. What if x was 5.01 or 5.000001? Well, take that number and square it. That's a number a tiny bit greater than 5. When you square it, you should get something a tiny bit larger than 25. And the closer we get to 5, while staying to the right of it, the closer we should be getting to 5 squared as a function value. And so the limit as x approaches 5 from the right of this function, also 25. And since the limit from the left is equal to the limit from the right, that's our definition of the two-sided limit, the limit as x approaches 5, existing and being equal to 25. So the two-sided limit also equal to the 25, because the limit from the left and the limit from the right are both 25. Okay, consider this function instead. H of x is x squared if x is less than 5, and x plus 20 if x is greater than or equal to 5. And in particular, take a few minutes and see if you can compute the limit as x approaches 5 from the left of this function, the limit as x approaches 5 from the right of this function, and the two-sided limit as x approaches 5 for this function. So really pause the video, take your time, see if you can compute these limits. Excellent practice for your homework. And then when you're ready, start the video up again and we'll do it together. Okay, numerically, if you pick a number like x equals 4.999 and you plug it into this function h, well, 4.999 is less than 5, so it's the top rule that applies, and we get 4.999 squared, which is very close to 5 squared, and the closer we get in our x value to 5, but to the left of 5, the closer we're getting to 5 squared, which is 25, and that tells us that the limit as x approaches 5 from the left is 25. And similarly, if we pick numbers like 5.0001, well, that's a number that's greater than or equal to 5, and so it's the bottom rule that applies. And so we get 5.0001 plus 20, which is 25.0001, but you can see that the closer you get to 5 from the right, the closer you get to 25 as a value for h. So the limit as x approaches 5 from the right of h is also 25. And since the limit from the left and the limit from the right are both 25, that tells us that the two-sided limit is 25. And finally, consider this function, r of x is equal to x squared if x is less than 5, and x plus 9 if x is greater than or equal to 5. And once again, consider the limits as x approaches 5 from the left, as x approaches 5 from the right, and the two-sided limit as x approaches 5 of this function r of x. Pause the video, take a minute or two, compute these values, and then when you're ready, turn the video back on and we'll do them together. Just like before, if x is less than 5, if we pick values for something like 4.999 or something like that, then we're talking about the top rule, and we get that the limit as x approaches 5 from the left is once again 25 for the same reason it was in the previous function, and so we get that that is 25. In this case, if x is greater than, as x approaches 5 from the right, so if x is greater than 5 and pick a value like 5.0001, well, we use the second rule for this function, x plus 9. 5.001 plus 9 is a number a little bit bigger than 14. And the closer we get to 5 from the right, the closer the function value is getting to 14. And so the limit as x approaches 5 from the right is 14. And since the limit from the left and the limit from the right are not the same, we get that this two-sided limit does not exist. Okay, you should now be in pretty good shape to do the algebraic homework problems. I would like to take a look at some graphs and see how these techniques work graphically. I want to start by looking at this function, f of x equals e to the 3x minus 1 all over x. And in particular, I'd like to consider what happens to this function as x gets close to 0. If you tried to plug in 0, 3 times 0 is 0, e to the 0 is 1, 1 minus 1 is 0, so you'd have 0 in the numerator, and you'd have 0 in the denominator. Well, you're not allowed to divide by 0, so that would make this function undefined at 0. It's certainly very strange, 0 divided by 0, and we'll talk more about functions of that kind of form later in the semester. But what happens to this particular function as we get close to 0, we're going to look at in more detail right now. If we pick x values close to 0 but to the left of 0, like negative 0.1, negative 0.01, etc., so we're approaching 0 from the left, you can see that the function values appear to be getting closer and closer to 3. And if we pick x values close to 0 but to the right of 0, like 0.1, 0.01, 0.001, etc., so approaching 0 from the right, you see that it also looks like the function values are getting closer and closer and closer to 3. Since it appears that the limit from the left and the limit from the right are both 3, since that's what it looks like to us anyway, we could guess that the limit as x approaches 0 of this function is equal to 3. And that is indeed the case. Here's a graph of this function. This function is not defined at 3. That's why there's that little open circle where x equals 0 and y equals 3. But it is defined everywhere else, and you can see that as you get closer to 0 from the left and the right, the function values really do get closer and closer to 3. So the two-sided limit is equal to 3, and our guess was correct. I want to look at one more example. The function f of x is equal to the sine of pi over x. Once again, this function is not defined at x equals 0 because you can't divide by 0. And if we pick values close to 0 but to the left of 0, like negative 0.1, negative 0.01, negative 0.001, etc., just like we did for the last function, we find that the function values are all precisely equal to 0. Similarly, if we pick values approaching 0 from the right, like the values you see here, which are the ones we picked last time for the previous function, we also get that the function values are precisely equal to 0. So it certainly looks like the limit from the left and the limit from the right are both 0. And so we might guess that the two-sided limit for this function is equal to 0. And it turns out that that is, in fact, not the case at all, not in the least little bit. As x approaches 0 from the left or the right, the function actually oscillates wildly back and forth between negative 1 and 1, faster and faster the closer it gets to 0. It's oscillating between negative 1 and 1 for all real numbers, and just happening quicker as we get closer to 0. And what's happened is the values we've chosen for x just happen by bad luck to be values where this function crosses the x-axis, misleading us into thinking that the values were always going to be 0, or at least close to 0, for this function. But in reality, it takes all the values between negative 1 and 1 over and over and over again. And so the limit as x approaches 0 from the left or the right doesn't exist. Neither limit exists because it's not getting closer to any real number. It's just going between -1 and 1 faster and faster. And so that last example was intended to show that this technique we've been using of picking numbers and plugging them into the function and seeing what you get to guess at values for limits is really quite insufficient, and we need something better. And so that is what we are going to be shooting for next. Next lesson we'll come up with other ways to be more precise and confident about the values that we compute for limits. See you soon.